In this video, I will teach you how to find dy dx when y is not by itself in the equation, and also I'll teach you how to take the derivative with respect to other variables besides x. This is called implicit differentiation. If you appreciate the content, please give it a like. This is the equation of a line. Right now it's written implicitly, which means that x and y are on one side of the equation together. In Algebra 1, you were taught to write the equation of a line explicitly by getting y by itself. For example, if we subtract x from both sides, we're going to have y over, I can't see that. We're going to have y over 2 is equal to negative x plus 3. And then, if you were to multiply both sides by 2, you would get y is equal to negative 2x plus 6. This is the same line, but now it's written explicitly, meaning y is by itself. Right now, this equation is written implicitly. It would be very easy to write it explicitly by adding tangent to both sides, and we get y equals tangent x. This is an explicit equation like we're used to. Here's another implicitly written equation with the x and y together on one side. Let's see if we can get y by itself to write it explicitly. Subtracting 2x from both sides, we have y to the third power is equal to negative 2x plus 5. Taking the cube root of both sides, we get y by itself, and now the same equation is written explicitly. We usually would write an equation explicitly if we wanted to find dy dx. Now we could take the derivative of both sides. For example, for this one, we would probably write it with a 1/3 power and then go on and do the power rule and the chain rule. This little tiny equation right here is written implicitly with the x and y together. It would be very easy to get y by itself by dividing both sides by x. Y is equal to 8 over x. Now this is an explicitly written equation. We could easily take the derivative if we did a quick rewrite, 8x to the negative 1 power, and that's normally what we would do. The reason why we need another strategy besides trying to always write an equation explicitly with y by itself is because of equations like this. Take a moment and think about how you would get y by itself on one side of the equation with everything else on the other side. I mean, we could move the 2 secant y to the other side and take the cube root, but then y would be over here under the cube root. It wouldn't be by itself. So this equation would be very difficult to write explicitly. Yet we still need a way to find dy dx. Basically, we do not need implicit differentiation as long as the variables match. If we have a function of x and we are taking the derivative with respect to x, no new method is needed. We would just do the power rule, and this would be 2x, and done. It doesn't matter that we have a different variable now. As long as we are taking the derivative with respect to that variable, it still works exactly the same way. The derivative of y squared with respect to y is 2y. No new method needed. But how do you take the derivative with respect to x of a function that is written in terms of y? What do we do when the variables don't match? This graphic is foreshadowing because we can actually apply the chain rule to allow us to take the derivative when the variables don't match. In a minute, I'm going to show you that you've actually done this before. But let's start with a familiar example. We would normally show the derivative of this equation using the Lagrange notation, the one with the prime. The derivative of y is y prime, so that's the left side. For the right side, we're going to do the chain rule. First, you take the derivative of the outer function. The derivative of sine is cosine. You leave the inner function unchanged. And then you multiply by the derivative of the inner function. So that's 3x squared. So that's normally how we would do it. The Lagrange notation, the one with the prime, is sort of limited because it only works when these variables match. We were taking the derivative with respect to x, and here we have a function of x. But in order to prepare for when the variables don't match, let's go through it again using Leibniz notation, the one with the dy dx. In fact, the derivative of the left-hand side is dy dx, and the derivative of the right-hand side, here comes the chain rule, cosine x is the outer function. We leave the inner function unchanged, and I'm going to sort of show this extra step here. We multiply by the derivative of the inner function. So I'm going to say d dx, because of the Leibniz notation, of this x to the third power. Of course, we would go on to write cosine x to the third power times 3x squared as the final answer, but that's not the point of this lesson. Let's move on to one where the variables don't match. We are taking the derivative with respect to x, but the function is written in terms of u. As before, let's start with the familiar Lagrange notation with the prime. Taking the derivative of the left, that's y prime. The derivative of sine is cosine. And we're going to do the chain rule because we have this u and not just an x. So we put u, but then we write times u prime. So you've seen this before because this is just the memorized rule for the derivative of the sine function. We often write our derivative rules with the chain rule sort of built into the rule like this, u and then u prime. So this is really not brand new to you. That's how you handle it when the variables don't match. You simply tack on the chain rule. But we use Leibniz notation instead of Lagrange. So running through it again, the derivative of y is dy dx. The derivative of sine is cosine. And then we multiply by the derivative of the inner function. So d dx of u. Now, the derivative of u with respect to x is simply du dx. We don't actually write it off to the side like we would with a whole function. For this last one, I want to show you how this chain rule business still works even on functions where we normally don't think of it as a chain rule problem. Obviously, the derivative of y would be y prime if we're doing the Lagrange. The derivative of sine is cosine. But imagine that we wanted to just do the chain rule every time, even when we don't really need to. We would have x, and then we would say times x prime. But what is x prime? Well, the derivative of x is 1, which we don't really write, which is why we normally just write this. I mean, without the dot. Very quickly, let's look at it with Leibniz notation. dy dx is equal to cosine. The inner function is the x, and then we would multiply by the derivative of the inner function, which would be dx dx. You can probably intuitively see that, of course, dx dx is 1. They basically cancel out, just like in algebra. My point in showing you this problem is to show you that the chain rule always works, even on problems that we normally wouldn't think of as a chain rule problem. So as we learn this implicit differentiation, it's going to be safest to think of every problem as a chain rule problem. Worst case scenario, a dx dx or a dy dy will show up and you just cancel it out. For the next 3 problems, we are going to differentiate both sides with respect to t, not x. And this is why we don't use the Lagrange notation, the one with the prime, for implicit differentiation. F prime of x automatically means d dx of f of x, the derivative with respect to x. There is no way to express d dt of f of x, the derivative with respect to t, using the f prime Lagrange notation. So we're going to have to stick to Leibniz from now on. I did not mean to imply that we are going to use the dy dx notation for the rest of the whole course, just for when we are doing implicit differentiation, like when the variables don't match. So, the derivative of y with respect to t is dy dt. And then here comes the chain rule. The derivative of sine is cosine, and we leave the inner function unchanged, but then we multiply by the derivative of x with respect to t. So that's dx dt. And that's as far as we can go. On the next one, the variables do match, but don't overthink it, just do it the same way as we did before. The derivative of y with respect to t is dy dt. And here comes the chain rule. The derivative of sine is cosine. The inner function is t, but then we multiply by the derivative of the inner function with respect to t. So that's dt dt. Guess what we're going to do with this? Well, this cancels out, which we don't really need to write. So we would just put this. But that's exactly what I mean when I say it's always safe to do the chain rule. Worst case scenario, the chain rule part just cancels out. So let's do this last one. On the left we have dy dt. Here comes the chain rule one more time. The derivative of sine is cosine. The inner function is x to the third power. But then we multiply by the derivative of the inner function, not with respect to x. So we're not going to just put 3x squared. We are taking the derivative with respect to t. So let's go ahead and show this step. d dt of x to the third power. So we have to do the chain rule again to take the derivative of x to the third power with respect to t. The derivative of the outer function is 3x squared. The inner function is the x itself. If we were taking the derivative with respect to x, then the derivative of the inner function would just be 1. But we are not taking the derivative with respect to x. We are taking the derivative with respect to t. So the derivative of x with respect to t is dx dt. And this is the final answer. Pause the video and try these two problems by yourself. So we're going to do the chain rule. So the derivative of the outer function is 2y, but then the inner function is the y, and we are taking the derivative with respect to x. So the chain rule piece is the dy dx, the end. For the next one, now we are taking the derivative with respect to y. I encourage you to just keep doing the chain rule no matter what. So first we take the derivative of the outer function, and then we multiply by the derivative of the inner function. The inner function is just y, and the derivative of y with respect to y is dy dy. These simply cancel each other out. I'm just going to leave this with another step for our notes, but in practice, when you notice that it's dy dy, you will just erase it. Let's do one more of these. This time we are taking the derivative with respect to t. The derivative of the outer function is 2y times the derivative of the inner function, which is dy dt, the end. We are going to gradually level up to more and more complex equations for the duration of this lesson. Let's differentiate both sides with respect to x. So on the left, it will be dy dx. On the right, we are going to use the chain rule. The derivative of the outer function is 6x. The derivative of the inner function with respect to x would be dx dx. Don't leave it like that. Either don't write it at all, but if you wrote it down, erase it. Leveling up a bit. Still taking the derivative of both sides with respect to x. On the left side, we definitely need the chain rule. So the derivative of sine is cosine. And then we've got this inner function, but because of the chain rule, we need to multiply by the derivative of the inner function. With respect to x, that's dy dx. That's the derivative of the left. On the right, again, we do the chain rule. 2 times 3 is 6, so 6x is the derivative of the outer function. The inner function is just x. So we multiply by dx dx. We are taking the derivative with respect to x. You don't actually need to write this down. I'm just showing it for instructional purposes. Actually, let me be more explicit about my instructional purposes. I'm trying to model for you that it's safest to think of every problem as a chain rule problem. Students often have a hard time learning implicit differentiation because they're not sure when do I need to do the chain rule and when do I not need to do the chain rule. So oftentimes they neglect to do the chain rule when they should. But if you just always do the chain rule, and if something cancels out, it just cancels out, then you won't forget to do the chain rule. So again, this is the final answer. Example C, let's differentiate both sides with respect to t. So applying the chain rule, the derivative of the outer function is cosine, the inner function is y, and we multiply by the derivative of y with respect to t. So that's dy dt. On the other side, we again take the derivative of the outer function, which is 6x, but then we multiply by the derivative of the inner function, which is just the x, with respect to t. This time it doesn't cancel out, so it's a good thing we got into the habit of doing the chain rule every time, so we wouldn't forget now. By the way, this graph is what this equation looks like. As we practice our implicit differentiation, not only do we have to do the chain rule, but we often have to do the product rule and the quotient rule. So don't forget about all the other rules that we've learned. Go ahead and pause the video and try this one by yourself. We are going to differentiate both sides with respect to x. So the derivative of sine is cosine, and the inner function is x. So if I did the chain rule with respect to x, it would be dx dx, but that cancels out and I'm not going to actually write it down. Moving on to the next term, the derivative of the outer function is cosine, but the inner function is the y. And the chain rule demands that we multiply by the derivative of the inner function with respect to x, which is dy dx. So, if you get into the good habit of doing the chain rule every single time, you won't forget this piece right now. And then the right side of the equation, the derivative of the outer function is the 2y. The inner function is the variable y itself. So we multiply by dy dx, and that's your chain rule piece. Can you tell the extra step we will have to take for this problem? I'm hoping you can see that we are going to need the product rule. Do not simply take the derivative of each one of these parts. You have to do the product rule. We have this yellow function times the blue function. So according to the product rule, we sort of go through this twice. The first time through, we take the derivative of the first function. The derivative of sine x is cosine x. And then if we do the chain rule, don't forget we are doing the derivative with respect to x. So the derivative of the inner function would be dx dx, but that cancels out and we don't write it. The first time through, you leave the second function unchanged. And then you put a plus and you run through it again. The second time through, you leave the first function unchanged, and you multiply by the derivative of the second function. The derivative of sine is cosine. the inner function is y, so the chain rule demands that we multiply by dy dx, the derivative of the inner function. This time it doesn't cancel out, so you have to be sure to do it. So this is the derivative of the left side. We had to do the product rule. Moving on to the right-hand side, the derivative of the outer function is 2y, but then the inner function is y itself. So we multiply by dy dx, the derivative of the inner function. And this is the final answer. Please pause the video and try to do this one by yourself. So, start with the derivative of the outer function, which is cosine. The inner function is the xy part. But then we have to multiply by the derivative of the inner function. Aha! Again, we are going to have to do the product rule. We have the x and we have the y, the yellow and the blue. So we are going to have to go through this twice. The first time through, we take the derivative of x with respect to x, which is 1. We leave the second function unchanged, which is a y, and then we put a plus. The second time through, we leave the first function unchanged, and we take the derivative of the second function. The derivative of y with respect to x is dy dx. So there's your product rule to take the derivative of this inner function. On the other side, as we did before, the derivative of the outer function is 2y times the derivative of the inner function, which is dy dx. So that is your final answer. Let me show you how to find the tangent line for a function like this that is written implicitly. You begin by differentiating both sides with respect to x. So the first term, the derivative of the outer function, is 3y squared. But we have to multiply by the derivative of the inner function, which is just a y, so dy dx, the derivative of the inner function. The derivative of a constant is 0, so that's gone. And then we have equals. The derivative of x with respect to x is 1. It's dx dx, so that's a 1. I'm just going to bring down that minus sign. The derivative of sine is cosine. That's the outer function. The inner function is the y. And we multiply by the derivative of that inner function. With respect to x, that's dy dx. It's actually rare that the directions just ask you to differentiate both sides with respect to x. Usually we have to keep going and find dy dx in terms of x and y. So somehow we have to get dy dx by itself on one side of the equation. I'm noticing that we have this dy dx here and here. So the first step is to get both of the factors that involve dy dx together on the left side of the equation. So I'm going to add this entire term to both sides of this equation, effectively moving it over to the left. So now we have this. With both terms involving dy dx on the same side, we can now treat dy dx as a common factor. We can factor the dy dx outside of parentheses as a GCF. So I'm going to pull out the dy dx to the front, and that's going to leave behind the 3y squared and the cosine y. And this is all still equal to 1. We need to get dy dx by itself, so I'm simply going to divide both sides of the equation by 3y squared plus cosine y. So dy dx is equal to 1 over 3y squared plus cosine y. Now it's time to write the equation of the line tangent to the graph of this equation, the one we started with here in yellow, at the point 2, 0. We always write the equation of our tangent line in point-slope form, so we know we need a point and the slope. Well, they gave us the point. The point of tangency is 2, 0. So all we need is the slope. In calculus, the slope comes from the derivative. So this expression will give us the derivative at any point, including the point 2, 0. Now, be mindful of your notation. We are going to evaluate this derivative at the point 2, 0. So don't just go plugging in the 2 and the 0 without using the notation that shows that you're about to plug something in. It goes like this, dy dx, and you put a vertical line, and then at the bottom of the vertical line, you put the 2, 0. This is mandatory. Now you can plug in the 2 for x and 0 for y. Well, there are no x's, so we're just plugging in 0 for y. So we have 1 over, plugging in 0 for y right here is going to wipe this term out, so that's just gone. So I'm going to go ahead and show this step, cosine of 0. Cosine is the x value on the unit circle, and at 0, which is right here, the x value is 1. So the slope is 1 over 1, which is 1. Now that we have a point and the slope, we can write the equation of the tangent line. It goes y minus y, so that's y minus 0, is equal to the slope times x minus x. So that's x minus 2. This is a perfectly valid equation, but I would feel silly if I didn't simplify this a little bit. I can ignore the 0 here, so I have y equals, and I can ignore the 1, so that's just x minus 2. Here's a graph demonstrating what we just did. This blue curve is the graph of this implicitly written equation, and this is the line tangent to the curve at the point 2, 0, the line y equals x minus 2. The last thing I'm going to teach you in this lesson is how to find the location of any vertical or horizontal tangent lines for an implicitly written equation. For context, here's a graph of the equation. We can see that there are some horizontal and vertical tangent lines. For example, there's one right here. We're going to find the location of points such as this. The first step is to find dy dx. So we need to take the derivative of both sides of this equation with respect to x. The first term will be 2y. That's the derivative of the outer function. But we do have to multiply by the derivative of the inner function, which is just y. And the derivative of y with respect to x is dy dx. And for the next term, the derivative, we bring down the 4. And then the derivative of y is just dy dx. Moving on to the right-hand side, the derivative of the outer function is 12x squared. But one more time, we need to multiply by the derivative of the inner function. With respect to x, though, that would be dx dx, and these just cancel each other out. So as soon as we notice that, we erase it. Don't leave it. Erase it. We need all the terms that have dy dx on the left side of the equation, but they're already here. So we can move on to the step where we factor out the dy dx as a GCF. So that's going to leave behind 2y plus 4. And this is equal to 12x squared. Dividing both sides by 2y plus 4, we get dy dx equals 12x squared over 2y plus 4. You will have a horizontal tangent line wherever dy dx is equal to 0. And you will have a vertical tangent line wherever dy dx is undefined. Remember, dy dx is this rational expression, this fraction. A rational expression will equal 0 when the numerator is equal to 0, and it will be undefined when the denominator is equal to 0. So we can find the horizontal tangent lines by setting the numerator 12x squared equal to 0 and solving. Dividing both sides by 12, we get x squared is equal to 0. Taking the square root of both sides, we have x is equal to 0. That's the x-coordinate. What about the y-coordinate? Here's the original equation. If we want the y-coordinate that goes with an x-coordinate, simply plug in the x-coordinate into the original equation and solve for y. Show that you are about to plug in 0 by writing the phrase at x equals 0. So I'm plugging in 0 right here. Y squared plus 4y and plugging in 0 right here will just give us 0. We can solve this equation by factoring out a common factor of y. So that will leave y times y plus 4 is equal to 0. Setting each of these factors equal to 0 gives us y equals 0 and y equals negative 4. Combining these two y values with the one x value gives us the following ordered pairs. 0, 0 and 0, negative 4. We say the given equation has horizontal tangent lines at 0, 0 and 0, negative 4. And sure enough, here's the point 0, 0 with its horizontal tangent line. And here's the point 0, negative 4, another horizontal tangent line. Similarly, we can find the location of the vertical tangent lines by setting the denominator of dy dx equal to 0. So let's set 2y plus 4 equal to 0. Subtracting 4, that's 2y equals negative 4. Dividing by 2, that's y equals negative 2. We found the y-coordinate of the point of tangency, but we need the x-coordinate to go with it. So let's plug negative 2 back in for y in the original equation. You can't be plugging things in willy-nilly. You have to show that you're about to plug something in by writing at y equals negative 2 first. This is mandatory. Substituting negative 2 for y gives us this. Negative 2 squared is 4. 4 times negative 2 is negative 8. Equals 4x to the third power. 4 minus 8, so we have negative 4 is equal to 4x cubed. Dividing both sides by 4, that's negative 1 is equal to x to the third power. Taking the cube root of both sides, we get x is equal to negative 1. Pairing this x value with the y value we already found gives us a point of tangency of negative 1, negative 2. Adding on to what we wrote before, and a vertical tangent line at negative 1, negative 2. Let's take a look at the graph. Sure enough, here is the point negative 1, negative 2, and here is a vertical tangent line. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.